So our next speaker is Monalisa Singh Roy from Bar-Ilan University. Please, 20 minutes with questions. I'll raise 5 minutes.
Yes. Just give me a minute, please. Okay. Hello, everyone. I thank the organizers for giving me the chance to speak here, but most of all, thank you for still being here. So I'm Monalisa Singh Roy, and Monalisa is my real name. So this is our ongoing work with Jonathan, Emanuele, and Efrat. And in this, we are going to visit something very basic. So we are not going to present a lot of results, not because we don't have a lot of results, but mainly, we will ask some basic questions and hint at an answer. So let's go. As basic as it gets, we all know here that the total entropy of a system generally increases until we act on it to contain that. But is that always true? Well, let's look at some of the popular examples in textbooks. If we start from a very particular ordered state and we let that thermalize, then we know that with time it will be thermalizing away from an ordered state. And unless that is we act upon it to make it do otherwise. For example, if we constrain it with some particular kind of Hamiltonian dynamics, for example, antiferromagnetic interactions, then we shall see that it goes to a particular kind of ordered state. But even then we know that at high temperatures, when there is more scope to thermalize, it will again get disordered. So this much is known, and known are also the methods of classifying that level of disorder. So everybody here knows about entropy, and the way we calculate it, as has already been shown, we can, okay, so if this is the x-axis of the system, we are considering only one-dimensional system of, say, spin-half particles, and the vertical axis shows the growth of time. Then at any given time, if we want to calculate the entropy, we just divide the system into two parts, trace over the degrees of freedom in one part, and the energy spectrum that we get out of the reduced density matrix that gives us this very nice measure of von Neumann entropy. So this quantity right here gives us a very nice measure of disorder. So when a system is naturally allowed to thermalize, we know that it becomes as disordered as possible, meaning that the measure of disorder, entropy keeps growing as much as the entire volume of the system would allow. Why the volume? Because once it has reached a maxima, it has become as disordered as possible, then there is no further scope to increase it, even if you wait for more time. So this is directly proportional to the system size. Again, no. So this naturally begs the question that what happens if instead of just letting it evolve, we monitor the dynamics of the system. Now what we mean by monitoring here is that these are just two qubit gates on these Penhub particles, and after application of, say, any such gates, if we fix one of the spins to a particular projected state, that means from the reduced density matrix, we are losing some matrix elements which would have related this to the next time step. So in a sense, as if we are freezing this and disturbing the evolution. So that is still okay, at least in this case, because there is one measurement, the system can still get disordered and talk to the next time step matrices through other bonds. But if the measurements are supposed to frequent, then we would expect that the dynamics is disturbed. How disturbed? Now, there have been many literature, but in particular, Nahum et al. Compared this kind of system with the percolation problem, where they show that if each of the spin system, each of the spins at any given time, if that could be vertex, and all these connections could be graphs of the vertex, then any projective measurement is equivalent to cutting off all these links. So which reminds us of 2D percolation type of problem. And they showed that if there are frequent measurements, then eventually we disconnect one part of the system from the other. So they stop exchanging information. And that is when this goes from earlier disordered entangling phase to a disentangling phase. So it's well known now that if the frequency of such measurement is low enough, we are still in entangling phase in which the entropy growth is proportional to time and scales as the size of the system. Whereas in the disentangling phase, because we already disconnect one part of the system from the other part, no matter how much time you wait or if you increase the system size, there is not much scope for the entanglement to grow. So it saturates like an area law. Whereas at this transition, we have this critical dynamics in which this entanglement scales as a log law. So these are a very well-known result today, which makes it slightly boring. So among the new things, new questions being asked here are some very recent works by Dalla and Shero groups, among others, in which they showed that in some particular kind of system, when there is still some kind of monitoring, particularly of this sort, what this means is there is a dissipation term that we are using instead of the projective measurements. It corresponds to the no-click or post-selection kind of method. They showed that instead of this kind of one point where we see this logarithmic scaling, just the transition point, they get this whole phase where we see these kind of log growth. And for some very high values of this dissipation rate. For example, in this, we can clearly see that there is a log-like growth with the system size instead of the volume law up to very high values of these dissipation rate. Whereas at really high values of the dissipation rate, we finally get this kind of area law. So this is really special. So we know that in general, we always see a transition from an entangling phase to a disentangling phase in a monitored system. But here they showed that they get this phase, this entire thing goes missing, this gets extended, and of course we go to disentangling phase with faster rate of monitoring. So the question is, we have the trivial case here and the special case here. So how do we go from here to here? What connects this? So that is the question we are asking. So our way to try to find an answer to that is first, in addition to this kind of integrable model, now we have integrability breaking, we have the same mode of dissipation, which is a post-selection method, and we have just this term for even more scrambling at each step. So what we do here is, after the application of each of the gates, which corresponds to all these, we have dissipation at each of the sites with this given rate gamma. And with this kind of setup where we have this model as well as dissipation, we hope to find an answer to what happens in between. So first off, we find that at no dissipation, we have the volume law as expected, where the system grows as a function of the system size. And at very high, not very high, but high enough gamma, we see that we have recovered the disentangling phase, which is the area law. Because since it's after a certain critical threshold, it doesn't matter anymore what system size we go, it's simply area law. But something strange came up in between, that is for intermediate values of a measure dissipation factor gamma, we find these kind of transients in which we don't see these kind of nice monotonous growth with system size, neither the area law, so something in between. So this is a bit perplexing to us. Firstly, we do not find any kind of log law kind of critical phase. Instead, 5 minutes? Okay. Instead, we have this kind of transient regime between these two well-known phases. So to confirm what is happening here, we go to some model which is even more scrambling than these two. So this is simply the model with random unitaries. So just to revise what we saw here, we find a volume law at 0 dissipation and area law at high gamma and in between some kind of transient. But to confirm what is really happening, we go to a much more random system in which for the gates, we simply have random unitaries here. All these gates are replaced by random unitaries and the dissipation factor is here as before. So here we find that for 0 or very low dissipation factors, we have this nice volume law, whereas for higher values of dissipation, we go back to the area law. And we found that the transition happens somewhere around here. Even here, we did not find any extended logarithmic scaling. So based on all these, this is simply at even higher gamma, the area law holds. So based on all these, our guess is that the condition where there is an extended log-law kind of region and log-law to area law transition, that is a very special case. That's not as common, and that the trivial volume law to area law transition, which we see in the entirely random unitary case, as well as by breaking integrability, need not be necessarily connected to it. So, okay, we would really like some ideas here if somebody has it, and we would be happy to answer questions. Thank you.